edge computing in space from Ranveer and Shadi. So Ranveer actually is the managing director for research for industry and the CTO of agri-food at Microsoft. He also leads the networking research group at Microsoft Research, Redmond. And Shadi Noghabi is a senior researcher in the networking research group at Microsoft Research. She received her PhD degree in CS from University of UIUC in 2018, where she worked on the design and development of several large-scale production systems. So let's welcome these two speakers.
Thank you so much, Shishong, and happy Diwali, everyone. If you see me dressed in these colorful clothes, it's because it's Diwali, and Diwali is a festival in India, and so I'll have to step out in the middle. I think we're running late. I had booked this until 7, but I'm really excited to be talking to you all about some of the work we have been doing at Microsoft, in Microsoft Research, on space and space-related systems. So today I'll be talking about some of the work we've been doing together with Shadi and some of the other people. As I said, the work it spans different teams across Microsoft. Lily's working with us, as well as Debopam in India. The other people, Microsoft Research in Cambridge, Tushar is in India. And there are people, and we work with various professors, with interns, as well as program managers who are helping us with Spectrum. We've launched a satellite as well. That I'll briefly mention as part of the talk too. So there are many applications for Earth observation systems. So today I'll mainly focus on Earth observation. For example, precision agriculture, monitoring events like floods, crop stress, or climate change. And for example, you could use Earth observation from space to track ships, how they are moving, tracking supply chain as it is moving through the supply chain as well. Satellite images are often used for disaster monitoring. For example, there were recent floods in Pakistan, to wildfires in California. There are many such applications of Earth observation that you already know about. One way to get the view of anywhere on Earth is through satellites. That's what's happening. For example, some of you are sitting in Asia, some of you are sitting in the US. You might want to know what's happening in Europe at the same time. The way to get that information is either through satellites with cameras or sensors, which can see the Earth from space, or using IoT satellites that can connect sensors on the ground to the cloud. For example, for maritime or for precision agriculture. Satellite IoT connectivity is required to connect 80% of the planet's surface that does not have terrestrial internet access. The other set of applications is from remote sensing satellites. These are satellites that have cameras or other types of sensors in them that are critical to sense what might be happening in different parts of the world, either through like monitoring floods, or you're monitoring crop canopies, greenhouse gas emissions, and other parameters. So together, through remote sensing and through sensors on the ground, we can get a view of what's happening anywhere in the world. In this talk, we'll focus mostly on Earth observation satellites. A typical Earth observation satellite these days will operate in low Earth orbit. These orbits are 500 to 1,000 kilometers above the Earth's surface, and they have a period of about 90 minutes. And as you see, these satellites continuously go around the Earth and they scan the surface very much like drones do in the sky. And modern Earth observation satellites have three very interesting capabilities. First, because they operate in very low orbit, they can give us very high resolution images. Today, we can get imagery where each pixel maps to less than a meter by meter on Earth. There have been many proposals which have brought this down to even further, much more higher resolution, and we'll see even further resolution over the next years. The other thing is for IoT, these sensors can directly connect to these low Earth orbit satellites as well. And earlier I showed just one satellite in the previous image. If I have just one satellite and I need to get an image of my house, it can take 5 to 10 days, depending on what the orbit is. However, these days, companies are deploying really big satellite constellations. So it brings down the time between images to a few minutes. And finally, as we are getting more hardware on these satellites, you can fit more and more capabilities, not just about monitoring RGB spectrum, but these days you can get multispectral, and some of them are also sending hyperspectral based sensors on these satellites to space. So as these satellites go to space, what does a typical pipeline look like of getting images or sensor data from anywhere on the planet to our data centers? So these days, through Azure Orbital, we've built these ground stations that are co-located with these data centers. One of them you're seeing here is in Quincy. You're seeing a few more as well. You also get satellite IoT, these IoT sensors that can connect directly to satellites. They send all of this data to these ground stations that are located close to the data centers. This data then flows inside, where you then have orbital analytics, which is you can then start running artificial intelligence on that data, be it camera data or sensor data, to then start deriving insights on top of that. So towards that, one of the key challenges, if you look at the entire end-to-end pipeline, is all the way from the beginning, where IoT systems right now, they don't scale. You can only connect so few sensors to satellites at any time. Another challenge is the remote sensing satellites. They collect large amounts of data, but you can't really send them to the ground because you don't have the bandwidth. There is also a high latency of sending all of this data to the ground because you don't have the bandwidth. And finally, AI training is slow and it is limited by the data. So as a result, from the time an observation is made from anywhere, an event happens anywhere on the planet, to the time you generate the insights, it's a few hours to sometimes even days, depending on where that event has happened. Our big bet within this project that we are all part of is how can you make these end-to-end insights from space happen in near real time, of the order of minutes. From the time an event happens, can you get a notification that that event happened? In our team, we've been working on various parts of the entire value chain to bring down this latency to a few minutes. On the IoT side, we are coming up with new spectrum sharing techniques from using which you can increase the number of sensors that you can connect to space by 2 orders of magnitude. We are running, instead of sending all of that data from satellites down to the ground for processing, we are running edge compute in space, which Shadi will talk about today. The other challenge is, rather than sending all of that data down to a single ground station, we have come up with a new way, a distributed ground station architecture, which was in SIGCOM last year, where you have hybrid ground stations of low cost and expensive ground stations, using which you can reduce the latency to a few minutes. And finally, rather than training on the ground, one of the new things we've come up with is this concept of fed space, where instead of training in data centers, you can run these training pipelines in space, in satellites, using federated learning. So with that, I wanted to hand it off to Shadi in the team, who's leading our work on edge in space.
Thanks. You see the changes, right? Okay. Yeah, thanks for the handoff, Ranveer. So today I'll talk specifically about how we are doing edge computing in space and focus on one of the projects that we have on that area. But first, I want to give a little background of why is it important to actually do computing in space and what is the big motivation. And the main reason here, as Ranveer briefly mentioned, is there is a huge downlink bottleneck. So on this chart here, what you can see is we took the Landsat 8 satellite, which is currently one of the well-known satellites taking imagery, and we just scaled what would happen if we had bigger and bigger constellations of this particular type of satellite. And as you can see, even for a single satellite, there's a huge gap between what the satellite can observe, meaning what it actually goes over the Earth and could capture potentially, versus what it is downlinking today. And because of this limitation, these satellites are even more selective as to what they observe, and they just don't collect the data in the first place. And this gap just gets worse and worse as you go into bigger constellations, which is a current trend because of the need of getting more frequent images. So if you want like daily images, even you need constellations of at least 50 or 60 satellites. So what we have been looking at is how can we mitigate this downlink bottleneck? And it seems like the most intuitive choice would be that how about we don't send all of the data? So can we be more selective about what can be sent? And can we filter out the data that is not of high value right at, sorry, I don't know what happened. I think somebody took control of the presentation. Can you see my slides now?
Yeah, we can see the
Okay.
slides.
Yeah.
It's 15.
It's on the filtering. Yeah, okay, thank you.
Yeah.
So as I was saying, so we want to be more selective as to what data are we actually sending. And as we also observed is a lot of the data is actually not necessarily of high value, even when they're sent down to Earth. Like, for example, over 2/3 of the Earth is always covered by clouds. And these clouds, for most applications, have very little value. And today what happens is after they download the images, when they check the clouds on Earth and even discard the data afterward. Another example is like areas of the Earth that rarely change, so there isn't much additional information gained by sending those areas. And what we are looking at in this work is how can we use that limited bandwidth and just filter out the low value data. And what we're focusing on is using the compute on space, which is a new trend of being able to put more compute, more especially like these commodity off-the-shelf compute, to do this. So I'll talk about one of the projects that we're doing specifically on Edge in Space, and this is about smart compression and how can we just compress data in a more efficient way. So one thing that's unique to satellite imagery is that things rarely change. Here you can see two images. One is an area like in September of 2018, and the same area captured a month later. And as you can see, there's very little changes. So if you look very closely, you can find some minor changes, but overall, there is very little that has happened. And what we're trying to do in this project is only download those change areas rather than just simply downloading everything. And we studied a big data set with like over 200 100 by 100 kilometer areas, and we found that on average, like around just 5% of the areas actually change. And if we are smart about it, we can compress the image by like 16.5x. So that sounds really great on paper, but the problem is that for you to do these kind of change detections, you have to have historical images. And the way that things are today is you have lots of satellites, each capturing parts of the data and going over the area for a certain period of time, and all of this data gets sent down to the Earth. And while on the Earth, we have this very rich data set of historical images, and you can look at time series and how things have changed. On the satellites themselves, we don't have that. And what we're trying to do in this work is to bridge that gap where we're trying to leverage that really rich data set and information that's on the Earth on the satellite itself. So why is that challenging? First of all, it's not just that our downlink capacity is very constrained. Overall, the entire environment of satellites is very constrained. So first, we don't have a lot of uplink bandwidth, so we can't send these big historical images very frequently to the satellites. And even if we do, there's not a lot of disk storage. So as Ranveer showed initially on that small animation, the satellite is constantly moving around the Earth and capturing different areas. it usually takes like 3 days or weeks to even get to the same location that it started off with. So now it means that you have to have a lot of these historical references for a huge area of the Earth. And simply put, the satellites don't have that kind of capacity or the uplink to even upload these historical references frequently. And what we do here is we are very smart about how we use these limited resources. First, we tried a bunch of different approaches, but we realized that we don't need the full resolution image all the time. And we can actually downsample by a factor of 16, like having a 4x4 downsampled reference for every pixel that we have. And also, we looked at a historical trace of how things change, and we realized that we don't need to constantly send these new images, and we can reuse the same historical reference for up to a month without significant degradation in our change detection. And these two simple things by itself can reduce our bandwidth by almost 100x. So here you can actually see some results of what happens if we just do downsampling. On the x-axis, you can see the compression ratio that we achieve by using downsampling, and the y-axis is the percentage of changes that were detected. So we compare to, if we were to compare full resolution images versus if we compare downsampled images. And you can see with like almost above 99.9% accuracy, we're still able to detect the changes. So as I said, like you can downsample images and still achieve very high compression and accuracy. And that brings us to our second challenge. Okay, so now you have the reference image and you're above those system limitations, but the whole environment is a very dynamic environment. So even though you have a reference image, it doesn't map one-to-one. And there are many unpredictable dynamics in that environment that make your capture image different than your historical reference. Like here, for example, you see on the left, you see a captured image, and it's the same area of the reference image on the right, but they visually look very different. Part of it is because of clouds, which are a dynamic part, and as I said, like between 2/3 to 3/4 of the Earth is covered by clouds at any point of time. And what we have to do is we have to discard these clouds, and we discard them because often most satellite imagery applications don't use them, even after they're downloaded. The other part is the illumination is very different, and because of that, you can't just simply compare pixel to pixel, and you have to do certain adjustments and transformations before you can even compare it to images. And this is where the edge computing really comes to save us, where we have a processing pipeline where we start with an observed image. The first step we do is cloud filtering. And so cloud filtering by itself can be very expensive. And because of that, we have specialized models, and we have different type of models depending on the context and the land that's underlying there. So we have models for oceans, for land, for forests, and that way we can have specialized and more lightweight models. We then adjust the illumination by using, like looking at the reference image and using linear regression approaches to adjust the illumination of the captured image and the reference image. And finally, we detect changes of pixels that have changed. And within those areas, we encode them and download only the changed areas. And just in case, just to safeguard against, potential errors and the fact that we don't want to never get new images down to the Earth, we guarantee that we have a download of the raw image, whether we detect changes or clouds or not, once a month. And that way we have a certain guarantee on the quality that is always being downloaded. And while all of this sounds very interesting, now instead of having a downlink bottleneck, we incur a new compute bottleneck because these satellites also have very limited compute. Part of it is because of the weight limitations they have. Part of it is because of the energy and power constraints that they have. And again, we use a bunch of approaches to make sure that we are able to do all of this within the compute limitations that we have on space. First, we make sure to use very cheap algorithms and specialize them, as I said, for different contexts. Like, for example, we use decision trees for cloud filtering, we use linear regression for illumination adjustment, and just pixel-to-pixel comparison for change detection. The other thing is, even for the compute, we do it on a lower resolution version of the image. And while these decisions can introduce more error into our detection, what we do is we always err on the side of caution. So if we're ever in doubt that something is cloudy or it has changed, we always just download it. And while that doesn't allow us to reach our full potential of 16x compression, we still can get 5x compression, and that's quite a lot of improvement over the state of the art today. So I'll just show you a quick demo of the system here. And this chart here just summarizes our results over a greater area. So we actually monitored 12 locations, each 100 by 100 kilometers for a 1 month period. And we measured our approach across the state of the art. So the state of the art today is just JPEG. We compared another baseline which could happen, which is if you have edge computing but only do cloud detection. And here on the x-axis, you can see the file size. So smaller is better. And the y-axis is the PSNR, which is like an indirect measurement of how well we're detecting, how well we're compressing, and how much data loss do we have through this compression, where higher is better. And as you can see, on average, we're able to get 5x better compression and higher image quality compared to this state of the art. And even if we focus only on areas that have really high cloud coverage, we're still able to get 2.5x compression. So with that, I want to conclude my talk here, and I just want to give an overview again. So as Ranveer mentioned, edge compute in space is just one of the areas that we are focusing on, and I've mentioned one project that we're doing in that space. We have a lot of different efforts going on in the group, from ways to do better spectrum sharing on IoT satellites, distributed ground stations, where we are looking at how to have more ground stations and use them better, and also even training in space and federated learning in space. And we would love to hear from you, and if you're interested, start collaborating with you guys on any of these areas. And thank you so much.
Thank you. So I saw Yongqiang Xiong raise his hand. Maybe please go ahead.
Yeah, thank you very much, Shadi, for your wonderful talk. I have one question about the networking or transportation implication of your system. So we all know for those satellite communications, we often experience very long delay or even disruptions of the communications. So I'm just wondering, for your system, so is there any innovation or exploration? So previously, as we can see, around 20 years ago, there was a research trend on the so-called DTN, delay tolerant or disruption tolerant network. So I'm just wondering whether there was a new trend or new things coming from your system regarding those delay tolerant or disruption tolerant network for the satellite communications.
Yeah, so that's a very good question. So inherently, as you said, the satellite communications are not always present. So usually, like maybe every 90 minutes, which is the orbit around the Earth, we get to do one contact. I'm sorry, I don't know what's going on with the slides. Somebody took control.
No problem. So we can see without the slides. No problem.
Yeah. So somebody took control of the presentation, which is not me. So what I was saying is, so like every 90 minutes there is one contact at best, and that contact is like 5 to 10 minutes. So that is actually the core reason why we don't have good downlink connectivity, is the fact that it's very intermittent, and any system that's built for satellites has to be able to tolerate these intermittent connections. In case of our system, that is not the main focus, in a sense that that's not the main angle that we're looking at, is like how to be more delay tolerant, but we are embedding it into our system, and we are assuming some buffer where we might not be able to send this data down even for a whole day or so. So we have to like count for that in terms of the storage we have on the satellite. And one thing that we were thinking of at some point is like, how can you have some notion of like priority similar to what you have in caches, where if something doesn't get access for a while, or like it becomes irrelevant, so there's a time to live, and if it doesn't get downloaded, maybe a new image is captured and that has higher priority. An example of that would be like, okay, you had this data that's going to be downloaded, but now suddenly you detected a wildfire somewhere, and that, even though it's later captured, you want to send that data earlier. Does that answer your question?
Yeah, absolutely. Thank you very much.
Yeah. Sure.
Thank you. So I think we saw another maybe Kongjun Park. I think you raised your hand. Maybe please go ahead.
So basically, you did experiment with for downsampled image for the comparison of a previous image with the new one. But I'm curious, which comparison method did you use? And the reason I am questioning to you is that I presume that there are some images that are very slightly different from all the parts. I mean, they have some different luminance in all the places, then I think this will make some encourage some change. It makes some change in downsample's image. But did you have any thought that using some other metrics such as luminance values or something?
Yeah, so as you mentioned, illumination is a big issue. And before we even do any comparison, we fix the illumination. So the way we try to do it is we use linear regression and convert the current captured image to match the illumination with the historical reference image. And then we do a pixel-to-pixel comparison where we have a set threshold for the PSNR, and based on that, we compare the pixels. We did try other approaches as well. So one thing we did was like, we tried things like, can we, instead of doing pixel to pixel, can we just compare histograms of the pixels? So just flatten the image. But the problem with that is then we lost the geospatial, the aspect of it. And just now it's like a one-dimensional, you turn a two-dimensional image to a one-dimensional vector, and we got worse performance than just downsampling things. So just to clarify, our method is not lossless, so there can be loss, but even the state of the art is lossy. So the JPEG 2000, it does lose some data. So that's why at the end what we compare is the overall PSNR, if we are doing better or not.
Okay, thank you.
Okay, given the time limitation, we can only adopt 2 questions. And thank you again, Ranveer and Shadi, our colleagues in America, because I think it's too late for you. So thank you again for your fantastic talks. Yeah.